In this section we're working with the derivative still, and we can still use all the shortcut rules that we have before, but now we're kind of looking at an application of the derivative, and that is the derivative as a rate of change. Typically when we talk about a rate of change, we could be talking about the average rate of change, or like we tried to find in previous chapters about the instantaneous rate of change. And now what we need to do is we need to distinguish between the two. Now when we say rate of change, we need to remember that we're talking about the instantaneous rate of change. And remember, ROC stands for rate of change. So we're going to get rid of that differences between average and instantaneous rate of change, just to realize that when we say rate of change, we mean instantaneous rate of change. So to get started, let's go ahead and look at an example. For this example, the rate of change, and again ROC is rate of change, of a circle is related to its radius by the formula A equal pi r squared. And of course this is a very familiar formula, area equal pi r squared. So the rate of change of a circle's, that should be circle's area is related to its radius by the formula A equals pi r squared. So the question is this: how fast does the area change with respect to, WRT means with respect to, the radius when the radius is 5 meters? So what ends up happening here, as the radius is increasing, then the area is changing at a different rate. And so if that radius is increasing faster, or we're going from, let's say, 10 meters radius up to 11 meters radius, that's going to have a different impact than if we were going from 100 meters radius to 101 meters radius. So the question is, how is that occurring? Well, what this problem is actually an instantaneous rate of change problem. So let's go ahead and look at our formula again. A equal pi r squared. Well, rates of change have to do with the derivative. So what we want is we want the derivative of area with respect to our variable. Now in this particular equation, the only variable we have here is r for radius. Pi is considered a constant. So I'm taking the derivative of area with respect to radius. Now again, the idea behind taking the derivative with respect to radius comes in right here. How fast does the area change with respect to radius? So we're working with radius here. If we had another variable, then we would have to be careful what our variable was here in the denominator that we were taking with respect to. So this looks like the derivative with respect to r of our formula for area. Well, area is pi r squared, and I need to take my derivative. So when I take our derivative, again, pi is just a constant, I drag it along. So I bring the 2 out front, so I have 2 pi, and then I decrease my exponent by 1. 2 minus 1 is 1, so there's an implied 1 here. This is kind of interesting because here we see we have 2 pi r, and if you're familiar with formulas for circles, this is the equation of the circumference of a circle. So that's kind of neat. The derivative of the area with respect to radius is actually circumference. So now what we want to do is we want to evaluate this at radius equals 5 meters. So a lot of times you'll see the notation evaluate at r equal 5 meters. So what we get here then is 2 pi times 5, or 10 pi. Now we're not quite done here, we need units. So what we have here then is the area, which is in meters squared, with respect to the change in radius, which is in meters. Now these units look funny. They look strange because here we have meters squared divided by meters. And that's because we have area divided by radius. But don't try and cancel the meters squared by meters into just meters, because that wouldn't make sense. This meters squared has to do with area over radius. So what I end up with here then is, how fast does the area change with respect to the radius? It changes with respect to the radius at 5 meters is 10 pi meters squared per meter. Now if you want a decimal approximation, of course you could come up with this, but this is an exact solution. So that's one application that we can look at with the derivative, is we can find out some sort of rate of change, instantaneous rate of change with respect to some other types of variables. Now one of the big things that we use radius for, or sorry, not radius, but derivatives for, is when we're talking about position, velocity, and acceleration. So this is how this works. We have a position function. The position function is usually denoted s of t in functional notation. So what this is position with respect to time. So if I was traveling with a particle along a path at time t, this would tell me where I was at in terms of position. Well, next thing I can look at is velocity. Velocity, I represent v of t, is the first derivative of the position function. And again, this is the change in position. Delta means change in position with respect to time. WRT is with respect to time. Now, if we're moving along a path, basically what we have here is we could have a change in position that's positive or negative. So let's go ahead and denote some other interesting characteristics of the velocity function. So basically this is how fast an object is moving. On a particular path, and this path is denoted by s of t. So it's how fast it's moving on a particular path. Now I could have velocity that's positive, and I could also have velocity that's negative. And you think, well, wait a minute, how could I have a negative velocity? Well, positive velocity means my object is moving forward, and negative velocity means my object is moving backward. So those are some interesting characteristics that we should kind of try and keep track of. Now, a lot of times when we talk about velocity, we're actually meaning speed. So that's another important thing to remember here, is speed is actually the absolute value of the velocity function. So if it's positive, it remains positive. If it's negative, we change it to positive. So again, speed is actually the absolute value of velocity. Now, if I want to take another derivative, the derivative of position is velocity, the derivative of velocity is acceleration. So acceleration is denoted a of t. It's the first derivative of velocity, or the second derivative of the position function. And basically what acceleration is, this is the rate of change at which a body's velocity changes as the acceleration is. So the rate at which a body's velocity, let me rewrite this. So the rate at which a body's velocity changes is the body's acceleration. Now there's one more derivative passed here, and that's called jerk. So jerk is j of t, and all of these are with respect to time. That's why we have the variable t here. That's the first derivative of acceleration, second derivative of velocity, third derivative of the position function. Now basically the jerk is a sudden change in acceleration. So that's what jerk is. And so when we look at this and we're talking about jerk, we have to talk about a sudden change. And so when we're talking about an object that isn't free fall, which we'll talk about here in just a second, it doesn't exhibit any jerkiness at all because there's no outside influences like drag. And so when we talk about the position function, a lot of times we're talking about it in terms of in a vacuum with no air resistance, with working with only like very dense or heavy objects. So let's go ahead and try and develop some of this by talking about that position function again. Now we're not going to fully develop the position function, but let's go ahead and get started. Again, the position function is denoted s of t, and like we talked about earlier chapters with Galileo's experiments, we kind of have an idea of an equation that represents an object's free fall. So we had 1/2 gt squared. Now what we have here is t, of course, is time, s is the distance fallen, and g is the acceleration due to Earth's gravity. So g is the acceleration due to Earth's gravity. Now if you look at this, I have two different values that I could use here for g. So one of these is g equals 32 feet per second squared. Okay, this is when we're using our standard units. I could also have g equals 9.8 meters per second squared, and this would be if I'm using English units or the metric system. So these are two values that come into play quite a bit of time. A lot of times I'll use 32 feet per second if I'm measuring things in feet, and of course 9.8 meters per second if we're working with things in the metric system. So what we like to do is we like to start with a problem that allows us to look through and solve a lot of these derivatives to come up with things like position, velocity, maximum height, acceleration, etc. So let's go ahead and write out a problem and see if we can solve it. So let's go ahead and read through the problem. A .45 caliber bullet is shot straight up from the surface of the moon, and it would reach a height of this function, this position function, s equals 832t minus 2.6 t squared feet after t seconds. On Earth, in the absence of air, its height would be this position function, s equals 832t minus 16t squared. So there's a little bit of a difference there. Now, this is going to be a distance in feet after t seconds. And the question I want to know is how long will the bullet be aloft in each case? Now this is kind of an interesting question, and we can also talk about what the shape of this particular trajectory is. If we think about this position function, this is a parabola, and I know it's a parabola because I have t squared here, and it's a parabola opening down because the coefficient is negative. So what ends up happening here, and both of these this is true for, this is some parabola. So here's the surface of the moon or the Earth, either one, and it's shot up and it comes down. It's a parabola that opens down. So this is at t equals 0, where it shot up, and what I want to do is I want to figure out how long the bullet will be aloft in each case. Well, if we follow the path of this bullet, it's going to be aloft from this distance clear down to this distance, and this is the distance or the time t that I'm looking for. This is my unknown. Well, if you think about it, in order to figure out what's happening here, I need to figure out where the position is equal to 0 for this end and for this end. And I already know t equals 0 over here, but I need to know when the position equals 0 again over here. So we have two cases. I have the case of the moon and the Earth. So let's go ahead and do the moon first. So I want to know when the position function for my moon trajectory equals 0. So in order to solve this equation, I can factor out a t. Factoring out a t, I'm left with 832 minus 2.6t equals 0. Now using the zero factor property, that tells me two things. T equals 0 or 832 minus 2.6t equals 0. Well, here's our case t equals 0 right over here. Solving for t here, I get t equals, subtract the negative, or subtract the 832 across for negative 832, divide by negative 2.6, and here I get t equals 320 seconds. And that's this value up here would be 320 seconds. So on the moon, the bullet would be aloft for 320 seconds if it followed this particular trajectory. Now let's go ahead and see what it's doing on the Earth. On the Earth, it's the same thing. I want to look at the position function, and I want to figure out where the position function equals 0, because where it equals 0 is when it hits, when it basically is shot off the surface and when it hits the surface again. So when I have it set equal to 0, I can use the zero factor property by factoring out a t, and I have 832 minus 16t equals 0. Zero factor property says that either t equals 0 or the other factor must equal 0. Well, t equals 0 is our initial position, so that's up here. Now let's go ahead and solve this one. Here I would get t equals negative 832 over negative 16. And in this particular case, I'd get 52 seconds. And so on Earth, I'm only aloft for 52 seconds. Now what could explain this? Well, there's more gravitational pull on the Earth than there is on the Moon, so it's pulling that bullet toward the surface of the Earth faster. So it's not aloft as long. Now another quick question we could answer is, on this trajectory, how high will the bullet go? Well, just as we have before, we have two cases. We have the case of the Moon, and we also have the case of the Earth. So let's go ahead and look at the Moon first. Well, if we think about the trajectory, and again I start here at t equals 0, and for the Moon I went to t equal 320 seconds, not that it matters. But when I was following this trajectory, I had some sort of a maximum height right here. Okay, so this maximum height is what I'm looking for. So how high will the bullet go? It'll go up to this height. Well, if you think about it, on this side, as I'm traveling along this path, velocity is positive, and over here velocity would be negative because you're falling back down. So I'm looking for the point where velocity is neither positive nor negative right here. And so this is where v prime of t, sorry, not v prime, just v of t equals 0. Okay, so v of t equals 0 is what I want. Well, what is v of t? Well, v of t is the first derivative of the position function. So our position function here was 832t minus 2.6t squared. So recall, s of t was 832t minus 2.6 t squared. So my derivative would be 832 minus, now when I bring the 2 down, I have 2.6 times 2, 26 times 2 is 52, so minus 5.2 t. And I want to set this equal to 0 and solve. Well, solving for t, I get a negative 832 when I move it across, divided by negative 5.2, and I get t equal 160. Now this makes total sense because a parabola is symmetric. So t equals 160 is when this is occurring. So it's occurring halfway through the trajectory. So I go up for 160 seconds, I reach that maximum height where I'm not going in the positive or negative direction, and then I start falling toward the surface of the Moon for the next 160 seconds. So it makes sense that this is the midpoint. But this does not answer the question. T equals 160 means it reaches its maximum height after 160 seconds. That's what this is saying. So in order to find that maximum height, or the maximum position is sometimes how you'll see that read, S sub max, that would be my position function evaluated at 160. Now remember, this is my position, it's not the derivative, so I plug it right in to my original position function. 832 times 160 minus 2.6 times 160 squared. And if you plug and chug through that, you get 66,560 feet above the Moon's surface. That's amazing. Now let's see how that differs with the height above the Earth. The height above the Earth, I would think, wouldn't go as high because the gravity from the surface of the Earth is going to start pulling that bullet down toward it a lot faster than it did on the Moon. Same setup, v of t equals 0. S of t for the surface of the Earth was 832t minus 16t squared. Okay, so I want my velocity set equal to 0. Velocity is the first derivative of position, which would be 832 minus 32t. So now again I want this velocity set equal to 0. In solving, I get t equals 832 negative when I move it across, divided by negative 32, and I get t equals 26 seconds. Boy, that's a huge difference. Now you might say, well, why is 26 seconds up here? Well, our curve is different. This is our curve for the Moon. Our curve through the Earth, remember, went up to 52. Half of 52 is 26, so this totally makes sense. So it will reach its maximum height after, or at, 26 seconds. So the maximum height then would be S sub max equals S of 26. So that would be 832 times 26 minus 16 times 26 squared. And if you plug and chug through that, I get 10,816 feet above the surface of the Earth. So these are my two solutions. Now, the one on the moon is so much higher because it doesn't have as much effect of the gravity pulling it back toward the surface of the moon. The one on the Earth doesn't go as high because gravity is pulling it constantly back toward the Earth's surface. Now the position, velocity, acceleration, and jerk functions are something that you'll see a lot when we're talking about derivatives, but there's also tons of other applications of derivatives in other areas of study as well. And we definitely can't cover all of them, but we'll just cover a few. We could also look at economics. So let's go ahead and look at an example from economics. When we talk about economics, we usually are talking about the cost or the production or the rate of cost or the rate of production. So we usually use a variable or an expression like C of X to represent the cost of producing X widgets. So again, C represents cost, X is the number of widgets that I'm producing. Then we start talking about things like marginal cost. Well, when you talk about margins in economics, usually it has something to do with a derivative. So marginal cost is the derivative of the cost function, or the cost of production. And basically it's a rate of change of cost with respect to level of production. So rate of change, ROC, of cost with respect to WRT, level of production. Now we can kind of think of this as the extra cost of producing one additional unit in a very general sense. So it's not the exact definition, but it can be thought of as the extra cost of producing one additional unit. In a vague sense. There's a little bit more to it than that, but that's, if you think about it like that, you can, usually figure out most problems. Now another function that we work with a lot of times is the revenue function. So a lot of times you'll see it written as R of X, and this is the revenue of X widgets. Now of course, if we talk about the derivative here, this would be called the marginal revenue. So let's go ahead and look at an example where we can apply these types of economic applications to our derivative. So let's, for this example, suppose the revenue from selling let's say X widgets, they could be anything, is given by the revenue function R of X equals 20,000 times 1 minus 1 over X. And of course this will say is in terms of dollars. The first thing I would like to do here is find the marginal revenue . Let's say when 100 widgets are produced. So I'm already producing widgets. What would be the marginal revenue at that very time when I'm already producing 100 of these widgets? What would it cost if I'm producing widgets at the rate I am right now of producing one more widget past 100? So that's kind of the question that we're looking at here. Well, remember, our function R of X is equal to 20,000 1 minus X to the negative 1. Now this is not my derivative. All I did is I took this X and I flipped it up top. So when I take my derivative, R prime of X, and remember we have a function and a derivative running around here, so I have to be sure and label those. I drag the 20,000 along. It's just my coefficient out front. Now I take the derivative of 1. The derivative of a constant is 0. And then the derivative of this piece, I already have a negative out front. I bring the negative 1 down, and then I decrease that exponent by 1 to give me a negative 2. So what I get here then is r prime of x equals 20,000. Now let's see what happens here. A negative times a negative is a positive, and then this x to the negative 2 flips. So this would be 1 over x squared, or my derivative is 20,000 over x squared. So this is my marginal revenue function. Now what we want to know from this marginal revenue function is what is my marginal revenue evaluated at x equal 100. So another way we could write that then is r prime of 100 equals 20,000 over 100 squared. Well, 100 squared is going to be a 1 with 1, 2, 3, 4 zeros. So that's 20,000 divided by 10,000 is equal to 2, and this is $2. So if you think about this, the marginal revenue of one more machine when we're already producing 100 machines or widgets is about $2. So you have to determine whether that revenue is worth it or not. Let's go ahead and look at another question. On this one, let's use r prime of x, the marginal revenue, to estimate the increase in revenue that will result from increasing production from 100 widgets. That's the one that we just found up above. 100 widgets a week, we'll say, to 101 widgets a week. So what we have here then is we have r prime of x that we've already determined. So here we have r prime of x equals 20,000. Now what we want to know over x squared is what is this evaluated at 101. So it'd be 20,000 divided by 101 squared. Now approximately this will be $1.86. So go ahead and square 101, divide it into 20,000, you get approximately $1.96. So the increase that we see here, the increase in revenue as the number of items increases to 101 is about $1.86. Now let's look to see what happened. When it was 100 up here, it was $2. For 101, it's $1.96. So it kind of almost looks like it's decreasing. The more items I produce, I'm not necessarily going to be making more money here, because my revenue function, if you look up at the original, kind of had an interesting characteristic. As x went toward infinity here, let's run back up here. As x went toward infinity, this went to 0, and then my revenue function went exactly toward 20,000. So that's kind of looks like my balancing point for revenue. Now, since we brought up the idea of a limit, let's go ahead and look at one more question here. Let's go ahead and find the limit as x approaches infinity, as in I'm approaching an infinite number of widgets that are produced, of the marginal revenue function. So this is the limit as x approaches infinity of 20,000 over x squared, basically. Well, we can see pretty clearly here, as x goes toward infinity, this overall fraction goes toward 0. So what's happening here is the increase in revenue as the number of items increases without bound will approach 0. So this is $0. So it doesn't pay off in this particular case with this particular function and these widgets to produce more and more and more past a certain point, because I will not end up making any more money. Let's go ahead and look at another example, and this is the classic example of draining a tank. So in this example, the number of gallons of water that is in a tank, T minutes, So we're in terms of minutes here. After the tank has started to drain, is given by the function Q of t. Q doesn't have any particular meaning here. Q of t 200 times 30 minus t quantities squared. Okay, so the tank has started to drain, and after t minutes, what I can do is I can plug in my value of t. So let's say after 1 minute, I could plug in 1 here. 30 minus 1 is 29 squared times 200, and that would give me an idea of how many gallons that were left in the tank. So if we wanted to figure out at t equals 0 what was happening here, I'd have 30 squared, which is 900. 900 times 200 would be 180,000 gallons as the size of my original tank. So first question, how fast is the water running out in this case at the end of 10 minutes? Okay, so if we want to know how fast the water is running out at the end of 10 minutes, what I need to do is I need to take a derivative. Okay, so I kind of want that instantaneous rate of change of the tank draining. So Q of t is my original function, and I want to take its derivative. Now I could use the chain rule here, except I haven't learned it yet, so I need to go ahead and rewrite this. I need to FOIL this out, first outside to insides last, and when I do that, I'm going to have t squared minus 60t plus 30 times 30 is 900. Now if I wanted to take my derivative, I could just drag along the 200. So Q prime of t, just drag along that 200. The derivative of t squared is 2t. The derivative of minus 60t is minus 60, and of course the derivative of a constant is 0. So I get Q prime of t, the rate of change that we have here in the gallons of water in a tank after t minutes, is equal to 200 times 2t minus 60. So that's Q prime of t. Now we want to know what's happening at 10 minutes. So we want Q prime at 10. So 200, 2 times 10 minus 60. So this is 200 times, 2 times 10 is 20. 20 minus 60 is negative 40. So what I get here then is negative 8,000 gallons per minute. Okay, that's a lot. That tank is draining very, very fast. So first of all, what's up with this negative value? Well, basically this means water is leaving the tank. That's what's happening here. So water is leaving the tank. So that's why I have a negative value. So it's leaving the tank, and you know, when it's draining, it's going to be draining at different rates. And exactly at 10 minutes, it's leaving the tank at a negative 8,000 gallons per minute, or it's leaving the tank at 8,000 gallons per minute. Next question we could ask here is, what is the average rate? What is the average rate at which the water flows out during the first 10 minutes? So what we're looking at here then is a question similar to what if you were driving your car, let's say between here and Wall, and let's say it takes you 60 minutes. Okay, and it's about, if we're traveling, we'd want to know about an average rate. So we'll say it's 60 minutes and it's about 60 miles. So that's about a mile per minute on average. Although what we're thinking about there is not at the beginning of the trip you might be going slower, and at some point you're going 80 miles per hour. But what ends up happening here is we have to be pretty careful about that we're figuring an average and not an instantaneous value. So the average rate of change that we're looking at here would be Q of 10 minus Q of 0 over 10 minus 0. This is the average rate of change. So this is from previous chapters. Well, Q of 10 would be our original function. It's not the prime, it's just Q of 10. So this would be 200 times 30 minus 10 quantity squared minus 200 times 30 minus 0 quantity squared, all over 10. Okay, when I work these kind of problems, I kind of like to look at them a little bit differently because I like to practice my algebra. This is going to be 200 times 20 squared minus 200 times 30 squared, all over 10. Now the temptation might be to start canceling some of these zeros, but we really can't do that unless we do some factoring first. So I'm going to factor out a 200. I'll be left with 20 squared minus 30 squared, all over 10. Now I can do some canceling. 10 cancels into 200 20 times. So this is 20. 20 squared is 400. 30 squared is 900. 400 minus 900 is negative 500. So I get negative 10,000 gallons per minute. That's the average. Sometimes it's faster, sometimes it's slower, but this is the average. Now when you're working with these problems, you know, these, I set up quite a few of these for you, but everyone's just slightly different, and you're going to have to look at the problem and identify exactly what the question is, and maybe draw a mental picture or use Maple to draw a picture to see what's going on. And you might even need to look back in your book at some examples as well, because we definitely cannot cover every single possible example in a lecture. So use your book as a good point of reference for setting up some of these problems.